Guess we can go ahead and get started. I think it's just going to be you and me, as per the always. Did you have any questions before we get started?
Um, no, I'm good.
I did mention to you that I pushed the test off till at least Tuesday night, or actually for your class, it'd be Wednesday night of next week, the
Okay.
online test.
All right. Oh, the online. Okay.
And the
Um,
face-to-face one next week will still be probably the same thing, but the online one will probably be pushed back as well.
all right. And then that will cover the face-to-face will cover chapters through 26.
Yes, the face to face or the online one that's happening that's due like Wednesday of next week or whatever, that should be through chapter 26. And then ideally what's happening is the following week we should be ready to do 27 and 28 hopefully.
Okay.
And then the final exam should include just up through hopefully 30. I would ideally like to get through 31, but it's probably not going to happen. But I'll
Okay.
cover it in some way, just won't be able to test you on it or anything. That makes sense?
Yeah. What is 31?
31 is sort of the synopsis where we put together all of Maxwell's equations and sort of
Oh,
explain how that makes electromagnetic waves, and we introduce the electromagnetic spectrum. You know, great excess undermines various industries. Marxism rules is the mnemonic I made up for the gamma rays, X rays, microwaves,
okay.
visible, ultraviolet, X ray, and radio. Or yeah, radio. So actually, no, it's not X-ray. It's the other way. Sorry. But yeah, that's the mnemonic I made up. So it covers that stuff. It's not that terrible of stuff, but it's sort of the most interesting part of all of chapters 21 through 30 is chapter 31. So that's the
Okay.
downside. All right, well, we'll go ahead and get started then. I have a problem written out, or at least the beginnings of a problem written out that we're going to solve, and it's an RC circuit problem. As far as my notes were concerned, I guess I just introduced you to the equations and then didn't actually do any examples. I thought I had done an example, but when I was redoing it this morning, it did not have an example. So I decided to start off with that. So let me go ahead and share my screen with you. And all I have right now is the statement of the definition of the RC circuit to some extent, but that's about it. There you go. So it says an RC circuit has a net capacitance and a net resistance of 0.200 nanofarads and 30.0 kiloohms and is powered by a 12.0 volt battery. So that's what the circuit's about. What we want to know is the time constant, so T equals question mark. Notice the wording I'm using here because I'm just putting symbols just to go through it quickly. But the wording I'm using is sort of the common parlance of the chapter, so you want to make sure you're aware of that as well. We would like to know what the maximum charge of the capacitor could possibly get is from this circuit. So I'm going to say Q max equals question mark. Part C, we want to know how long it takes to reach 99% of Qmax. So, how long before Q equals 0.99 Qmax? Okay, that's a really hard time fitting that in there, but anyways, 0.99 times the uh, Q max. And then part D, we want to know the current when Q is at half its maximum. So I equals question mark when Q of T is equal to 0.50, let's call it 500 Q max. So in other words, we will need to find the time at which the charge is 50% of the maximum that it'll reach, and then use that to determine what the current will be at that point in time. Part E, we want to know what is the maximum current. And part F, we want to know specifically the charge on the capacitor. So Q when The current is 20% of its maximum value. So Q when I equals 0.200 I max. And that's, typical me uh, making sure everything has three sig figs just because I hate it when an answer comes up with one sig fig. And it's a much more likely the fewer sig figs you have, the result will be fewer sig figs. So, anyways, that should explain more or less what the problem is. I'll draw the circuit real quick just to remind you what it would look like. So you can imagine a battery that is 12.0 volts that is connected to a switch that looks like this, and then it goes through a resistor like this, and then I'll say it turns the corner and goes through a capacitance C, and this C is equal to 0.200 nanofarads, and this resistor is 30.0 kilo ohms. So that gives us all the information we really need. I'll start off with the solution by stating the equations that we need to know. In this case, we're actually talking about a capacitor that's being charged up. So what we're imagining is the switch is open. There's no current running around the circuit. All of a sudden, you change the switch to closed, and that results in a positive charge fleeing away from the positive side of the 12.0 volts. And it's going to force it to go through the resistor and then start to stack up on the rightmost plate of the capacitor. That's going to build up slowly a positive charge. We expect it to sort of grow exponentially and asymptotically to the maximum value. But what's going to happen is as that gets higher and higher, it's going to compel more and more positive charges that are free in the left uh, plate of the capacitor and the wire to the left of it. It's going to compel those positive charges to run away, and they're going to actually go into the negative side of the battery. That's what happens. Even though no specific charge actually jumps from one side of the capacitor to the other, we still get something just like a current. And what we know is that the equations for these various parameters are the following. So, for instance, we have C is equal to Q over V. That's one of the equations we'll make use of. C is equal to Q over V. We know V, as in Ohm's law, is equal to I times R. And those things just sort of help us put together what we're trying to do. What we know is that the current is going to build up sort of asymptotically. We know that the charge is going to build up asymptotically, and or yeah, the voltage and the charge are going to build up asymptotically, and the current is actually going to exponentially decay. So, with that in mind, I can immediately say that the voltage across the capacitor is actually given by basically Q. Well, let me see. The voltage should be equal to this symbol right here is the symbol we use for the EMF. So it'll be E times 1 minus e to the negative t over RC. That's the equation for the actual voltage across the capacitor. And you can see that this equation basically has a voltage of E minus a exponential decay. So it's sort of like it's trying to start there, but at t equals zero, you get 1 minus 1, so that's zero, and then it builds up to it. Similarly, the equation for the charge looks the same way, and in fact, charge is equal to capacitance times voltage, so that's going to be CE times 1 minus e to the negative t over RC. And the RC, by the way, is the time constant, tau. So I just want to remind you of that. So it often is written as negative t over tau as opposed to negative t over RC. And then, as I told you, the current is actually going to be an exponential decay. And of course, current is equal to E over R. times, in this case, e to the negative t, and this time I'll write it over tau. So those are the equations we're going to be using. Now I'm going to go about solving them. You have any questions about anything before we get started?
Nope, we're good.
Okay. So first off, we're going to start with tau, which is equal to RC. And I did mention that you guys should know how to do this, how to convert the units of ohms times farads. You should be able to convert that to seconds pretty straightforwardly. I'll sort of hint at it a little bit in some of these examples, but right now I'm just doing the math. So what I've got here is 30.0 kilo ohms. And as I told you in electronics, often we just leave all the prefixes in there and work them out on the fly. That's what I'm doing here. We also have 0.200 nanofarads, which is 10 to the negative ninth, of course. And you can see 10 to the negative ninth times 10 to the positive 3 would be 10 to the negative 6, and that would be a micro. So we expect the results are going to come out as micro. If we actually multiply 30 times zero point 0.2, that's the same thing as 3 times 2, which is 6. So this is going to be 6.00. Of course, the rest of the digits would be 0 as well. So if we wanted more digits that weren't significant figures, that's what we do. We just put a bunch of zeros after it. But since the k times the nano gives us micro, we got 6.00 microseconds is the time constant. And as we mentioned in these exponential growth slash asymptotic growths of voltage and current, that means that in one time constant we'll go from 0% of the max to 0.63 of the max, and so on. So we've got that one. That's equal to the time constant. So I'll circle that. The next part is we'd like to know what is Q max. Well, what Q max is the largest value that Q could have. So we know Q starts off at 0. So what we're sort of thinking of is taking Q in the limit as t approaches infinity. So for part B, we can think like this. We can say Q max is equal to the limit as t approaches infinity of c times the electromotive force times 1 minus e to the negative t over tau. Okay, so if you look at that, what you see is the limit as t approaches infinity. This e to the negative t over tau is literally 1 over e to the t over tau power. And as t approaches infinity, with it being in the denominator, you can see that the 1 over e is going to go to 0. So we just get c times e, which is sort of the whole point. Basically, the circuit acts like the voltage or like the charge across it is just going to be equal to C times V. And that's basically what we've concluded. So when we see C times E, what we have to do is take C, which is 0.200 nanofarads, times E, which is 12.0 volts, and
Hold on,
12
wait, I have
times,
a question real quick.
go for it.
Since t is in the numerator, if we're taking the limit of t, wouldn't that go to infinity?
It does, but the fact that it's a negative exponent means we're
Oh
dealing
gosh.
with 1 over t e to the t.
Oh right, that's right, that's right.
That makes sense?
Yeah. Okay, so then that would go to 0. Okay.
Exactly. Yeah, and just to bring that home, we'll just say that part goes to 0. Okay. So 12 times zero point 0.2 is the same thing as 2 times 1.2, so that should be 2.4. And in this case, it's going to be 2.4 nanocoulombs. So we get 2.40 nanocoulombs is Q max. And I'll circle that as well. and that's the three sig figs. We can tell the remaining digits would be zero as well, so I'm not really losing anything by not carrying two extra digits. We'll go on now to part C, and part C wants to know how long before Q is equal to 99% of Q max. That's hard to read up there, but I think you can follow what I was saying when I wrote it, so let's go on with that. Now, the big part of this is really just reminding students how to solve equations that have logarithms and exponents in it. So really what we're doing is we're taking the Q equation, and for Q of t, we're going to replace it with 0.99 times basically Q max, and Q max was CE. So we put that on the left-hand side of the equation for Q, and then we write the right-hand side of the equation for Q, and we get CE times 1 minus E to the negative T over tau. So we can now see that the C times E cancels out on both sides. We can also realize that I can pull the E to the left-hand side, it'll become positive, and I can pull the 0.99 to the right-hand side, and it'll become negative, and we're doing 1 minus 0.99, so that's pretty straightforward what we get. It's going to say that E to the negative t over tau is equal to 0.01 because that's 1 minus 0.99. Now, the trick to solving this is anytime you try to solve for an exponent, you want to take a logarithm of the both sides of the equation. If you happen to have a logarithm whose base is the same as the base on the exponent, then you're really, really lucky because then you don't have to do any extra work. We have a logarithm that has e as its base, and that logarithm is called the natural log. So I'll take the natural log of both sides. We can imagine it like ln and ln like that. Now, when you take the natural logarithm of something raised to a power, the power comes out in front as a coefficient on the logarithm, and then you're just left with the logarithm of the base. And of course, the logarithm of e, I'll show you the one super important thing from logarithms that I've held on forever and helps you with just about everything you do with logarithms. I'll show you that in a second, but it should convince you that ln of e is 1. So in this case, what we're going to have is negative t over tau times the natural log of e, which I said was 1. So I'll stress that right here, is equal to the natural log of 0.01. And technically, you could see that as if it has three or any number of sig figs, really, to be honest with you. So if I take the natural log of 0.01, I should get a negative number, and it comes out to, make sure I have the right color on here, I get negative t over tau is equal to negative 4.60 and then 52. And those two are not sig figs, and I tried to space them in pods of three. So you see C605 is a pod of three followed by two. So hopefully that helps a little bit. And we can see the negatives cancel out so that T is equal to 4.60, and then the extra digits 5 and 2 times the time constant. And that's generally the rule of thumb. If you're looking for how long it takes for your capacitor to reach its max, it's generally five time constants. You're probably used a little bit to talk about standard deviation, and what we use in standard deviation and standard error is anytime a data point was three standard deviations away from the mean, you are in some sense statistically allowed to toss that data. In this case, it's sort of like it, but it takes more than three. It actually takes five for an RC circuit. So we could leave it like that, and that's a perfectly wonderful answer. But to be honest with you, I don't like it until you have it in seconds. So I'm going to take the 4.605 and multiply it by the 6 microseconds. So uh, 4.6052 times 6 microseconds gives me 27.0 0.631. Those are two extra non-significant digits, and this would be microseconds. So you can see, really, we don't have to wait any time at all to figure out or to find the capacitance fully charged. It's really going to take well under even a millisecond. So we have the answer to this. The answer is twofold. You can either call it the 4.61 time constants, or you can just say 27.631 microseconds. So that's the time required for it to reach 99% of its maximum. The next question we want to know is what is I when reaches its halfway point? In other words, when Q is only half the way. So we're going to do that now. Now, again, we're going to use the same equation for Q, but this time we're going to do it for zero point 0.5. So we're going to say 0.50, and that could be to any number of decimal places since we're specifically asking for exactly 5. So I'll just put it like this, and then, of course, the max would be CE, and then the other side of the equation is CE times, well, that E really looks bad. Sorry about that. Times 1 minus e to the negative t over tau. We can again see that the CE's cancel out, and we can also see that we get e to the negative t over tau is equal to 0.500 to any number of sig figs. This means that if you take the natural log of both sides, I happen to know because I'm one of those nerds, but it turns out that the natural log of zero point 0.5 is negative 0.6391. So I just happen to know that. So I'm going to get negative t over tau is equal to negative 0.6391. That's more than enough digits. So now I can see t is going to be equal to 0.6391 time constants. So in this case, it's well, actually, I think I can just leave it that way. That'll be fine. Yeah, I'll just leave it that way because we really don't need to know the time. We really are ultimately just looking for what the current is at that point. So we're going to see that they have, in some sense, a reciprocal relationship, and that's sort of what they're trying to show you with these two problems. But now that we know that that's the time, we can sort of look at it as just saying, oh, well, the exponent on E is going to be negative 0.693 or 6391. So that should help us a lot. Now what we're going to do is use the equation for I, and the equation for I is equal to E over R times E to the negative T over tau. So now we use I, which is what we're looking for, is equal to E over R times E to the negative T over tau. That's what we're using. We know that E over R is actually 12.0 volts divided by 30.0 kiloohms. And obviously that gives you a number in milliamps. So 12 divided by 30 gives me zero point 0.4 milliamps. And then that is times E to the negative 0.6391. And of course, you probably already know what 6391 is. But the main thing is, or e to the negative 0.6391. The main thing is we're going to do this calculation. So I've already got the 12 over 30 kiloohms gives me the zero point 0.4 milliamps. It's 0.400 milliamps. And e to the negative 0.6391 should give me 1/2. So now I'm going to type that out and say times shift E negative 0.6391, and that gives me, sure enough, 0.2. Ooh, that's actually surprising. Maybe I didn't carry enough sig figs, I guess. But 2111, and we should probably stick to 3 sig figs on this one, so I'm just going to say times this, and it turns out to be in milliamps. So the I at Q equals 1/2 Q max is equal to 0.21111 milliamps. And that's the answer to part E. Any questions on that one?
Nope.
All right. So now we got part F, or excuse me, that was part D. Sorry. I called it E, but it's D. So now, whoa. So now we have part E that's left. And we'll do that on the other side or the other page. And D is asking, or E is asking for what is Imax. And you can look and see that Imax is going to occur when T is equal to zero, because basically when T is zero, E to the negative T just becomes one, and you get E over R. And we know it exponentially decays, so it's going to get smaller from there on out. So I is just E over R, which we already calculated. So I want to write it right here. E I max equals I of 0, which equals E over R, which is 0.400 milliamps. So that's the answer for part E, and I was going to put it on the other side, but I could fit it there, and it's no big deal. It's really just a simple calculation. But what we want to know now is what is Q when I is equal to zero point 0.2 of its maximum. That's part F. So I'm going to write this. We want to know what is Q when I is equal to 0.200 I max. And this is part F, as I said. So, so what we're going to do is we say I is equal to E over R times E to the negative T over tau. And now I can plug this information in. I'm going to say 0.200 times E over R, which is I max, is equal to E over R times E to the negative T over tau. You can see from this that the whole point is the exponential has a value of zero point 0.2. In other words, e to the negative t over tau is zero point 0.2. And if you look at the equation for Q, Q is equal to, as we said before, it's C times E. Oops. C, ooh, that's really bad. It's C times the electromotive force times 1 minus e to the negative t over tau. So the fact that the e to the negative t over tau is zero point 0.2 tells you that 1 minus zero point 0.2 is going to be zero point 0.8, and that's zero point 0.8 of Q max. So we already know that it should be zero point 0.8 of Q max, and that's that reciprocal relationship I was telling you about between the current and the charge. Or it also applies to the voltage, where when the voltage reaches 80%, say, the current will only be at 20%, but when the voltage reaches 80%, the current will only be at 20%, that sort of thing. So that's really what we're going for here. Now that I have that information, I'll just go ahead and work it like I didn't know all that, but I just wanted to point it out to you. So now what I say is 0.200 is equal to e to the negative t over tau. And now I'm going to say Q at that time is going to be equal to C. Oops, I should have wrote C first. C times E times 1 minus 0.200, which equals 0.800 CE, which is equal to 0.800 times Q max, and we found that Q max was the 2.40 nanocoulombs. But the fact that it's zero point 0.8 was the more pressing detail here. So we can finally say that Q is equal to 0.800 Q max, but that's also equal to zero point 0.8 times 2.4, and that's 1.92. nanocoulombs. Any questions on that?
Now,
All right. So we also have the next example, which is an example regarding discharging a capacitor. So this will be example two. And in this example, like I said, we will be working with a charged capacitor. So we're starting off with a capacitor that is charged, and we're going to throw a switch, and the circuit's only going to have the capacitor and the resistor in it, no battery. But the capacitor is charged, so it has energy already. So as soon as you close that switch, the positive side of the capacitor is going to look just like the positive side of the battery, and it's going to compel all the free positive charges in the wire to run away from that particular side of the capacitor, and it's going to try to run away to the negative side of the capacitor, and in so doing, it's got to go through the current, I mean, through the resistor I as a current. Eventually, of course, all that energy is going to be dissipated through E equals I R, and you ultimately get zero. So the equations in this case should start off with the voltage being high, obviously the voltage being whatever the charge on the capacitor is divided by the capacitance itself. The voltage is going to be whatever the voltage of the battery that charged it up was, assuming it met the power requirements that were it was hit with, and then both the voltage and the current in the across the capacitor and in the capacitor is going to decrease in time. It's going to exponentially decay. Now, if you look at the voltage and the charge, you see that they're exponentially decaying. Well, what about the current? Well, the current's only going to run initially, and it's going to decay as well. So all of the equations for discharging a capacitor are the same. They're all exponential decay. What we're going to do though instead is we're going to say now that C is equal to 1.20 microfarads, and what we find is that uh, the battery voltage we're going to use is E is equal to 20.0 volts, so it is a little different. The capacitance obviously is a little different as well, and what we find is that the current uh, I is observed to decrease by 50% of, oops, by 50% of its initial value within, let's say, 30.0 microseconds. Okay. So that's the question, or that's the statement. A, what we want to know is what is Q at t equals 0? Part B is what is R for this particular circuit. So you see it's entirely different circuit because we have a different R in there. So what is R? I think you probably already suspected how we're going to figure out what R is. And then what is Q at t equals 60 microseconds? So C, what is, actually I'm going to do a different time. I'm going to do 50 microseconds instead. So what is, oh man, I hate this thing. It's always erasing stuff. So what is Q? Ah, darn it, did it again. What is Q at t equals 50.0 microseconds? Okay, so our circuit again, in this case, we're going to imagine we crank it up first with a 20-volt power supply, and then we just allow it to discharge. Okay, uh, let's start with solution. So the solution, we're going to have something for Q, we're going to have something for I, we're going to have something for V. I want to start with Q. Ah, darn it. I'm going to start with Q, and Q for discharging, of course, is just given by Q is equal to Q0 times e to the negative t over RC, which is also Q0 times e to the negative t over tau. The Q0 there, if we really had reference to like a previous circuit, we would just figure out Q as it is C times whatever voltage we charged it with. In this case, we're actually imagining the voltage that it was charged with was 20 volts, so we're going to figure that out as we go. We also need a voltage equation, and the voltage across the capacitor is equal to the initial voltage that the capacitor has on it, V0, which you can imagine is equal to Q divided by C. But that's going to be V0 times e to the negative t over tau. And then finally, in this case, the current is coming at the expense of the charge on the capacitor. So I is not dq dt, I is negative dq dt, and because of that, we end up getting uh, basically Q0. Whoa, Nelly, there I go again. Basically Q0 over RC times E. Dang it, there it goes again. Times E to the negative t over tau, which could also be written as I 0 e to the negative t over RC. So that's all the equations we're going to be using. Let's go ahead and start with part A, and that is what is Q at t equals 0. So we say C is equal to Q over V. That's our defining statement for what capacitance is. So we can tell that Q is going to be equal to what we call Q0, and that's going to be equal to C times V. The C, of course, is 1.20 microfarads, and the V is 20.0 volts. We can see that the 20 times 1.2 is the same thing as 12 times 2, so this should be 24.0 microcoulombs is equal to Q0. So I'll go ahead and circle that off. We now have part A. Part B is what is R? Well, what we discovered was that the thing came down by half in 30 microseconds. So we can use that with our equation for Q to find out exactly what the time constant is. And the time constant's R times C, so we just divide the time constant by C, and that'll give us R. So that's what we're going to do here. This is part B. What we have is Q is equal to Q0 times e to the negative t over tau. In this case, this means 0.500 Q0. That means the resulting Q, the left-hand side of the equation, is half of Q0 at the time we're looking for. And the right-hand side of the equation is just Q0 times e to the negative t over tau. And we actually know t here, so I'm going to erase that for just a second and put in what the t is. We found that this happened in 30. I thought I had said 40, but it's had happened in 30 microseconds. So what I'm going to do is put 30.0 microseconds over tau here for that equation. Now we can immediately see that the Q zeros cancel out, and then it's just a matter of taking the natural log of both sides. So we're going to do that. We'll say the natural log of 0.500, which we know is negative 0.6391, and that's equal to negative 30.0 microseconds over tau times the ln of E, which we know is 1. So I know that's really small. I wrote 30.0 microseconds times the ln of E. Okay, and this quantity, the ln of zero point 0.5, is negative 0.6391, and this quantity, the ln of E, is just 1. I still didn't give you that hint or trick that I said is so important with logarithms. I'll give you that right after this if I remember. So now I can get rid of the common negative that both sides has. Remember, there's a negative in front of the 30 microseconds, and then there's a negative corresponding to the 0.6391. So what I'm going to do is say 0.6391 is equal to 30.0 microseconds over tau. So tau, which is equal to RC, can be written as RC equals 30.0 microseconds divided by 0.6391. But we want R, not RC, so I'm going to go ahead and say R is equal to 30.0 microseconds divided by 0.6391 times C, which is 1.20 microfarads. Now that's nice, and that's why I did it, is because now we're canceling out the micro, and otherwise that might have been a little touch and go to try to figure out what's going on with the exponents. We could always just punt and change the prefix to 10 to the negative 6, but it's better if you don't have to do that. So that's why I went ahead and showed you all this. Now we've got R is equal to, I'm going to take 30 and divide it by parentheses 0.6391 times 1.20. And because the micros cancel out, I can just leave it as 1.20 and I get R is equal to 39.118. Now that should be 3 sig figs here, so that means the 1 and the 8 are not significant, and this gives me ohms automatically. Yep, that should be it. So that's our resistance. Now, regarding the log equation, I know it's in the middle of this, but just before I forget, y equals log base b of x implies both ways now, implies that x is equal to b raised to the y power. So you can see that if you take the log of e, and B is E, then you get E equals E to what power? And clearly the only way that E equals E to some power is if the power is 1. So that's why the natural log of E is 1. All right, now we've done part B. Part C is what is Q at T equal 50 microseconds. So that's pretty straightforward. C, we want Q at 50 microseconds. That's going to be Q0 times e to the negative t over tau. That is, of course, equal to 24.0 microcoulombs. And that micro could have looked better, but I think people could still read it. But just in case, I guess I'll go ahead and do it a little neater. So 24 microcoulombs times e to the negative, and I chose 50.0 microseconds divided by the time constant, which technically we haven't really figured out. We haven't computed that, but it should be R times C. So I'm going to put 39.118 ohms, which I'm not writing, times the capacitance, which is 1.20 microfarads. So that again fixes the micro issue. So I'm going to take 24.0. Well, actually, let's first figure out what the exponent, what the E is, because I need to know what the E is to the proper number of sig figs, so that I can multiply it by the by the 24 and get the proper sig figs. So if I take 50 and divide it by, that has 3 sig figs, divide it by 39.118 times 1.20. I know that answer should come out in 3 sig figs. So the answer is 1.06. 51 is the other digits. And in fact, we still got to multiply it by -1 and then raise e to that power. So I'm going to say times -1. And now I'm going to raise e to that power. So I'm going to say shift e to the answer, shift answer, and that's going to give me 0.3446 times 24. So I really want to write that. So I'm going to go ahead and write it as equals 24.0 microcoulombs times 0.34468. That gives me the two extra digits that I wanted. Even though that 6 looks really putrid. But that's what we're actually multiplying by the 24 now. So neither one of these are significant. So now I'm going to say times 24, and that gives me 8.2722 microcoulombs is the charge at that time. Any questions on that one? Sorry about that, Josh.
No, that's what I got too.
Okay, good deal. I'm glad you're calculating along with me. I know you would have eventually caught up why I had 1.06 and got so confused. It was all because I drew that little. You know what? It was because I did something stupid, which is I stopped to show you the logarithm thing, which made me completely forget what I was doing and not paying attention. And not only that, it's probably bad teaching to stop in the middle of a problem to teach you something. Uh,
You're fine.
one day I'm going to be a good teacher. I can feel it now. It's coming any day now. All right, so that's basically it far as the sections that I wanted to cover. But I really decided after talking to you the other night that I really do want to show you how to use a galvanometer to create a ammeter and a voltmeter. So I'm going to do that now. What I'm going to do is I'm first going to give you an idea of how a ammeter, or excuse me, how a galvanometer works, and I'll show you what a galvanometer often looks like in the lab. So for instance, if you're looking at a galvanometer, it would probably look something like this. It has sort of a little platform right here, and on there are your little inputs, if you will. So I will put an input there, and I'll put another input over. Actually, I want to make that input red. And then I'll put another input over here, and that one's going to be black. And it's usually just either a knob that you can put a U clamp under or something like that. But the main thing is we just know that it's going to be an input. Now, in addition to that, this device goes back this way, say, and ultimately it goes back to say here. And you can see basically what's going on here. But the main thing is right here, we have a needle that generally speaking just points straight up into the middle. But the scale is quite different. It has a scale that runs this way and this way. And this scale, for instance, might read 50.0, and this one would read negative 50.0. That's what the galvanometer looks like, and it's a pretty simple device. If we were to look inside of it, one way you could make one would be this. We're going to take and imagine a little chunk of iron, because it's nice and ferromagnetic. Take a little chunk of iron like this, and we'll mount it on a axle of some sort so that it can spin freely about that axle. And not only that, we might even have a lever associated with it that allows us to put springs on it to keep it from just spontaneously springing off the wrong direction. So we'd have a spring right here, and we'd have another spring right here, and they could be adjusted so that they always can be calibrated such that it would go to zero when no current's going through it. But here's the big thing. The red terminal that we had over here, we're going to take a wire straight from that, and we're going to run it here and let it go around this hunk of metal. Remember, it's a hunk of iron, and of course, we're making something very specific here. Do you remember what this would be when you wrap a current carrying wire around a chunk of iron? and then this runs back out to, of course, the black terminal, like that. So what happens there is when you're running a current through it, which I will indicate by this arrow here. Here's the current I. That's going through it, and that's going to make a magnetic field that points this way. And in fact, when a magnetic field points that way, remember I tell my students that magnetic fields are like old people. They leave the north and move into the south, just because everybody knows the story of people moving, to Florida or whatever. But the main thing is that's the same way that magnetic field lines go. So the bottom of this piece of iron is a north pole of a magnet, and the top of this piece of iron is a south pole of a magnet. So if I were to, for instance, put a north pole of a magnet over here, and I'll do it this way. So here's the north pole of a magnet over there. Soon as that current goes through that wire, that south end of the magnet is now going to be attracted to the north end of that other magnet, and it's going to deflect to the left, which is oh, excuse me, I meant to make it the other way. Let's change that to a south. Sorry about that. I forgot I put the negative to the left instead of to the right. So this end is going to be the south, and then over here we're going to have the north end of a magnet. So what's going to happen in this case is this top south end of the magnetic pole that's on an axle, that's going to be attracted to the right, and the stronger the current is, the stronger the magnetic field. And the stronger the magnetic field, the stronger the force of attraction it has to the unlike pole to the right. So in this case, it's to the right. If the current was going the other way, it would be to the left. And all you have to do then is just calibrate it. You just have to say, okay, let's put 50 microamps through it and see how far it deflects. And then, paint the front face to match 50 microamps right there. So that's how the galvanometer works. Does that make any sense to you?
Yeah, that does. And I also was looking up some pictures. Yeah, yeah. I mean, we use that a lot in lab, I guess.
Yeah, the first time you did it was in electric field mapping, and
Yeah.
that place is in that one you were setting it equal to zero by putting a probe on from one of the terminals at a dot in the field, and then you take the other dot, the other probe that was connected to the other terminal, and found out where you read zero, and then all the places that you read zero with that one made a equal potential line, so it made a line of constant voltage. So
Yes.
the problem with them though is, yeah, they're really wonderful and simple and you can work on them easy and that's great. But the problem is they're really delicate. So they only go up to like, 50 microamps, which is what this one is. So I'm going to say our galvanometer has a max current of 50.0 microamps and its resistance is R equals 10.0 ohms. That's a decent R figure. It's often you might have a single ohm or a couple of ohms or something like that, but I just wanted to make nice, easy numbers. So we're imagining we have this galvanometer,
Out of
and
curiosity, do they make galvanometers that have a higher tolerance for like a larger amperage?
I suspect they do, but I'm not sure they're that useful because we like the galvanometers being that small, specifically because we can teach you how to make a galvanometer that can measure up to any amperage, which is what we're getting ready to do in this example.
Oh,
Yep. So our example three here, design an ammeter. Oops. Evidently, there's two M's in ammeter that will use our galvanometer, but I darn it, but measures up to 5.00 amps. Okay, so that's our plan. Now, one thing it might help you to know is to know the voltage of the galvanometer. So, solution, what we're going to make use of here is Ohm's law, V equals IR, and we're also going to make use of the fact that V galvanometer is equal to 50.0 microamps times 10.0 ohms, which gives you, of course, 500.0 microvolts. Okay, so that's really what the volt is, and that's micro, so that's also equal to 0.500 millivolts. Technically, that last digit's not a sig fig, and that's 0.0050005 volts. Okay, now our plan is this. What we want is a wire coming in from the right or from the left going to the right, and we want that to have 5.00 amps. Now, what we have to do is in that 5 amp case, that should show full deflection on the galvanometer. So I need that wire to be broken up such that over here only 50.0 microamps goes through and runs into the galvanometer, which is, for all intents and purposes, acting like a resistor. Not a big resistance, but a resistor just the same. So we do that. Now, we can't just make that current disappear. In fact, you might even need it. So you don't want to do that. So what we have to do is we take the 5.0000000. I'm putting extra digits on here because I want you to understand that your calculator is not necessarily going to have enough screen space to do this by calculator. So sometimes you actually have to do the calculation by hand. So I'm going to take 5 amps and I'm going to subtract 50 microamps from it. So 50 microamps, by the way, is 0.000. That would be a milliamp to the end of that zero. Zero, zero, this would be 10 or a tenth of a milliamp, a hundredth of a milliamp, and then a 50 microamps. So the six, 1, 2, 3, 4, 5, 6 would be the micro, and I want 50 there. So actually, I've got to put the 5 right in that spot. So let's say 0.500 amps. That's 1, 2, 3, 4, 5, 6. Yeah, that's 10 to the negative 6 amps. You follow what I did there?
Yeah.
Yeah, it took it's easy to make a mistake on that, so I had to check it to make sure. So 0 minus 0 is obviously 0. That's not going to matter. This one's not going to matter. This one's not going to matter. But the craziness comes in again. This one's not going to matter. The craziness comes in when I have to borrow to make the subtraction of 5. That means this 5 is going to become a 4, and this is going to become a 9, and a 9, and a 9, and a 9 instead. So now I've got 10 minus 5 is 5, and then I got 9 minus 0 is 9, and then I got 9 minus 0, 9 minus 0, 9 minus 0, and then 4. So that's how many amps I need to go through the other wire. So what I have, oops, I hate this thing erasing all the time. So what I have here is a what we call a shunt resistance. So this is R shunt. And we have to have 4.99995 amps go through that. So what we have to do is figure out exactly what type of resistor will allow 4.99995 amps through it. And what we see is that shunt resistance is in parallel with the galvanometer. So we can say V shunt is equal to V galvanometer. And remember, the V galvanometer is what I just calculated. In other words, when 50 amps goes through there, it should have a whole voltage of 500 microvolts or zero point 0.5 millivolts. That's what we're using here. So in this case, what we're going to say is V shunt, which is 4.99995 amps times R shunt is equal to zero point 0.5 millivolts. Now, I didn't show all the sig figs there, but that's not really that big of a deal. I just need to solve for R shunt now. So R shunt is equal to zero point 0.5 times 10 to the negative third, because that's millivolts, divided by 4.99995. And that gives me 0.001000001 ohms. So that really is the resistance that we need to allow that 49.995 amps to go through there, and that would actually complete the design of the ammeter. So now, by having that set up, you can actually measure a current up to 50 amps. Now, the problem is you're probably not going to have exactly that right resistance. And not only that, it's approximately equal to 1.0 times 10 to the negative fourth, 10 to the negative fourth ohms. So that's just buying a 1 ohm resistor that's accurate 1 ohm is quite expensive, and it's a pain because it's 1 ohm, right? But what you could do is you could put a bunch of resistors in parallel, because what we know is when resistors are in parallel, the net resistance is smaller than the resistance of any one of them. So we could keep adding them up until we get a resistance value of about 0.001. But the main thing is we need to know precisely what it is, because every time we go to use it, we need to calculate what would actually be full deflection. Because if we didn't get exactly 0.000100001, if we don't have exactly that, it's not going to work out to be exactly 50 amps. The error might be small enough that it doesn't matter, but you got to check that. But that's basically the design for the ammeter made out of a galvanometer. Any questions on that?
Nope.
Isn't that sort of a cool idea to just have a extra path for it to run out?
Yeah,
And not only
definitely.
that, if you look at the galvanometer, next time you're in the lab, look at it and you'll see it'll have not only a 50.0 ohm scale, it'll have like a 25 scale, it'll have like a 100 scale, because they meant you to use all these different scales. So if you set it to a maximum of 5 amps, then you might want to use the 50 scale. But if you set it to a maximum of 100 amps, you want to use the 100 scale or the 10 scale or the 1 scale. Or if you set it to 250 amps, you might want to use the 25 scale. So that's why all those different scales are on the galvanometer, because they expect you to use it for a lot of different voltages and currents.
Huh.
Now we're
Interesting.
going to do the example four, and that's going to be, and you might have to leave or whatever, but I'm going to do example four, and that's going to be designing a voltmeter that will take, notice this one's only supposed to take up to zero point 0.5 millivolts. We're going to actually allow it to take up to 50 volts. So example four, is that four or five? Yeah, four. Example four, use the galvanometer to create a 50.0 voltmeter. Okay, so what we want is when the voltage that you're measuring is actually 50 volts, we want that to read 50 microamps. So what you need to think of is a wire that is coming in and is supposed to measure how much voltage is across the galvanometer. And what you need is the galvanometer, which acts more or less like a resistor. We need that galvanometer to only have a voltage drop of 0.500 millivolts. So we're going to imagine in this scenario that the voltage difference from here to here is 0.500 millivolts. But what we want to imagine is that this end, I should probably do that, I read, this end has a 50.0 volt voltage, and this end over here has a 0.00 volt end, and all we can put between it is a protective resistor, which I'm just going to call plain R. Now, what really has to happen is 0.500 millivolts is equal to 0.0005000 volts, like that. That's the drop across there, and we need 50 volts total. So 50.000000000 volts minus 0.0005000 volts. That gives you, obviously, all these are zero. This is zero. This is zero. This is 5 because this one becomes 10, and this becomes 9. This becomes 9. This becomes 9. This becomes 49. This becomes 4. So 10 minus 5 is 5. 9 minus 0 is 9. 9 minus 0 is 9. 9 minus 0 is 9. And then 49. So what we need is the voltage here. I need that voltage to be 49.9995 volts. So that's pretty straightforward. We also need the current I is equal to 50.0 microamps, because if it's not 50.0 microamps, it's not going to peak out the galvanometer. So now we know the current going through the resistor, and we know the voltage that the resistor has to have across it. So all I have to use is Ohm's law, and Ohm's law says V is equal to IR. So I need to figure out R is equal to V over I. We want the V to be 49.9995 volts, but we need the current to be 50.0 times 10 to the negative 6 amps. So this one's going to require a really big resistance, as you can tell. 49.9995 divided by 50 times 10 to the negative 6 gives me 999,990 ohms. So you can see that is really, really close to a full million. It's 10 shy of a million ohms. But if we do that, then we'll get full deflection at exactly 50 volts, and it'll work. So that is our galvanometer design. Again, once you put the resistor in there, you need to make sure exactly what the resistance is, because it's going to change the details of whether it's exactly 50 volts that causes full deflection, or whether it's in fact a slightly different, because you couldn't find exactly 999,990 ohm resistors. Does that make sense?
Yeah.
All right. Well, it's about time for class to leave. I wanted to show you guys some chapter 27 stuff. There's some very simple stuff in the very beginning. I think I'm just going to do that in video form, and you be prepared to ask me questions on Tuesday when you come back. But you can also ask questions before then. But like I said, sometime today the online test will be available as well as the practice test. But like I said, you have until Wednesday night to get that done. Okay.
Okay.
All right. Well, have a good one, Josh, and text or call or email if you have any questions.
Okay. All
Have a
right.
good
Sounds
one.
good. Have a good evening.
You too. And that's about it. We hit wood read. All right. Well, bye bye.